Good morning, everyone. I hope you guys were able to follow a little bit of what we have done so far when it comes to understanding what's NMR spectroscopy. We started by understanding that for a non-zero nuclear spins, there are a given number of states, degenerate states, which when suspended in an external static magnetic field would stop being degenerate. Now that you have integral non-degenerate energy levels, which helps you do spectroscopy, and we end up using radio frequency waves in order to change population across these states to get and learn some information about them. And the important aspect that we learned is that once you put a sample in, the sample generates a bulk magnetization that is parallel to the external static magnetic field that is being applied. Bulk magnetization gets developed for each of a non-identical spin that exists. And you would like to manipulate this in order to get as much information as possible from the system. In yesterday's class, we started to develop a bit of formalism. We first defined what is light. We defined it such that you have, it's 2b1 cos omega RF t plus phi along I. This is still in the lab frame. And the omega RF sometimes is also referred to as the transmitter frequency. And then this is the amplitude of the wave of the RF pulse that's being applied. And we decomposed this representation, the linearly polarized light, into two counter-rotating circularly polarized light. And therefore, we said the effective BRF is only going to be one of them that will interact. And the one that we chose to interact is the +1. The -1 would also be present. And just in case you guys might ask, does the -1 or the counter-rotating one, does it have any effect at all? Yes, it does have. As always in science, we tend to assume a few things and move on, but there are always exceptions to it. There are cases where the counter-rotating one also has an influence where instead of plus, it's a minus. And though that affects in something called Bloch Eqs shifts, which we won't go into in this course. It'll be more useful when you're trying to learn NMR and pulses in an advanced fashion, where the effect, if I remember correctly, goes like B1 by 2 B0 the whole square. So this would only matter for low fields or very high B1s that you end up applying. So for all practical purposes, the counter-rotating part of the RF can be conveniently ignored. And then we said, okay, this is the light that's going to interact with the matter that we have put in. And then for this, we invoked the time evolution of magnetization.
Can we also say that this comes into effect when we have homonuclear decoupling going on, right?
Yes, there are other, it also comes up in decoupling places as well.
The kind of experiments that we use is mostly there. Or do we have other experiments in biomolecules where we have to worry about this?
Correct. So there are places where you have to worry about it in the sense like as Jeet rightly pointed out in homonuclear decoupling cases. Yeah, totally agree, Jeet. Thank you. So dm over dt in the lab frame, this is the fundamental equation that helps you predict how the magnetization will change for an effective B. But this still is in the lab frame. Then what we did is to go to the rotating frame. Rotating frame is a sense of perception, meaning that we just want to negate the effects of precession about B0. And therefore, rotating frame is not real. It's just helping us not see something which always is there. As I gave an example of the noise, it's similar to the white noise that might be present all around us all the time, right? So the rotating frame, the equation modifies itself to dm over dt, rotating frame, which is going to be equal to dm over dt lab frame plus m cross omega, where omega is the angular frequency of the rotating frame. So basically, we set the rotating frame to the transmitter frequency so as to see what is going on. dm over dt in the rotating frame, therefore, reduces to something where B plus omega over gamma becomes the B effective in the rotating frame. Then the next series of discussions we had was that, let's say, we have applied the pulse along the XY plane as defined as the equation earlier. Now we are going to be in the rotating frame. I'm not going to write R anymore. Even the textbook tends to give it up at some point. So I'm also going to give up very soon on writing R every time. So let's say this is V1, this is the phase, and this is delta B naught that is being present. And therefore the effective vector is going to be the parallelogram law, where you end up adding these two to get the B effective along the plane containing B1 and delta B naught. And what was delta B naught? Delta B naught turned out to be minus omega over gamma. And then we also said the tilt angle that is present, theta. Theta will be tan inverse of omega 1 over omega, where the B effective, I should have written B effective first, but it's okay. In the rotating frame is going to be B1 cos phi times I, the rotating frame, plus B1 sin phi times J in the rotating frame, plus delta B naught along the Z axis in the rotating frame. So this is the effective B. And one of the steps that I realized I skipped was to understand what is the magnitude of B effective. That is going to be given by the dot product of B effective to B effective. If you go back and take a look, you're going to get square root of B1 square cos square phi plus B1 square sin square phi, because you need to take the dot product, meaning the same elements will get multiplied by each other, plus delta B naught square. So therefore, not under root, actually, yeah. So, okay, thank you very much. So therefore, this is going to be square root of B1 square plus delta B naught the whole square, where you know that tan theta is given by B1 over delta B naught. How did we write this? The theta is right here. If you take tan theta, it has to be opposite divided by adjacent. Opposite is B1, adjacent is delta B naught, and therefore you have this, and which implies delta B naught is B1 times cos theta divided by sin theta. So go back and put this back into this equation, then you will see that the B effective will be given by square root of B1 square plus B1 square cos square theta divided by sin square theta. So if you take the necessary LCM and all that, you will end up getting B1 over sin theta as B effective, magnitude of B effective. What is the origin of this delta B naught? The pulse that you apply goes with a certain frequency and a certain phase. The phase is determined by, with respect to x-axis, where did you apply, correct? Now, if you set the rotating frame frequency to the transmitter frequency omega RF, then the motion with respect to B naught precession will not be seen, correct? At that point, the effective field, remember, theta will therefore go to, if you set that, theta will go to 90. Why will it go to 90? The denominator goes to 0. Okay, tan theta of infinity implies theta is 90. If theta is 90, it indicates the entire effective magnetization in the rotating frame is along the pulse that you applied. When you have done that, do you see B naught vanishes altogether? On the other hand, as I gave you an example of ethanol, which has 3 spins, and each of the spin has different Larmor precession frequency due to changes in chemical shift. Larmor precession frequency is the same, but there is something called shielding and deshielding effect that comes that changes its resonance frequency in the NMR spectrum. Correct? So out of the 3 non-identical spins you have, you can only keep it on resonance at most at once with 1 spin. When you run an experiment, the carrier has to be kept at either the methyl proton or the methylene proton, the hydroxyl proton. You cannot keep changing as the experiment goes. So therefore, if you keep it at the methylene proton, the hydroxyl proton comes something called downfield to it, and the methyl proton comes something called upfield to it. So therefore, you see a non-zero offset, which is off resonance effects. Now, imagine when you were on the omega RF, the magnetization didn't move at all. It appeared stationary, right? But now let's assume I'm the hydroxyl proton, the carrier on the methylene proton. What is going to happen? The hydroxyl proton won't be entirely static. It will still have some motion. Slower motion than what it would have had in the lab frame, but it will have motion. And the methyl proton will have opposite motion because it's on the other side. And therefore, the delta B naught comes up depending upon how off resonance you are. Okay. If you have a positive off resonance, it will be on one axis. If you have a negative off resonance, it will be on the other side, minus Z. Did that make sense? So if you don't remember, let me show it to you again. So these are the three protons. You can keep it on resonance with respect to this, in which case it's going to be off resonance with respect to this. How would you determine off resonance? Off resonance will be determined by capital omega offset, which is going to be omega naught minus omega RF. Omega naught is kind of the precession frequency. Of course, it doesn't include the 1 minus sigma, which we'll talk about later. That's the shielding part. Omega naught for proton at a certain B naught is constant. That we are not questioning about, but changes come within the non-identical spin systems, which are not on resonance. And therefore, the delta B naught comes up. Did that make sense? This is still apparent, by the way. Basically, what it tries to say, it will still have some precession motion that is left that you couldn't cancel out after going to the rotating frame. Do you agree on that? It's an example of the carousel I gave, where you guys are going at an angular frequency and I'm also running with you. If I run as fast as you, we are relatively at zero speed with respect to each other. But let's say your carousel is going faster than me, then I'm going to lag behind. So I'm at a negative relative velocity with respect to you, or you are at a positive relative velocity with respect to me. On the contrary, let's say you're going at a speed, I'm going faster, similar arguments of relative velocity works out. That's what is rotating frame here. The rotating frame goes at a frequency, and if the spin's frequency matches or doesn't match, if it doesn't match, it's going to be faster or slower, would determine the direction of delta B naught. And the direction of delta B naught and B1 would end up determining the direction of B effective. Why did we spend so much time trying to understand how B effective comes up? Is because magnetization M will precess about the B effective. All motions in NMR are precession. That's it. Which is why I'm spending a lot of time trying to make you guys understand what is precession.
For BRF, we have chosen the plus sign.
That's correct.
So does it have anything to do with gamma?
Yes.
If gamma is greater than 0, then alpha is the ground state.
Yes, that's correct.
And if gamma is less than 0, then beta will be the ground state.
That's correct.
Then in that case,
the precession, direction of precession would be different from gamma positive and negative. Exactly. So that's why we want to understand both components exist, and at least one component interacts with the precession motion that you have. That's the whole idea. I just chose plus. You can literally have the same argument with minus. Nothing what we write will change. Literally, instead of having plus here, this will become minus. The magnitude will not change at all because you're having a mod square, right? Dot product. None of the other discussions will change. The XY component will be whatever it is, just that the Y component will be opposite. Think once again. Let's say in the carousel, you guys are going clockwise, and I'm running clockwise with you. It will have more effect than me running counterclockwise. And all I try to tell today is that the counterclockwise also has an effect, which is rather small for most of the cases. Yeah?
small, so we are neglecting.
Yeah, we can neglect. See, once again, we can go into details of everything, but this is not an advanced NMR course. This is a basic NMR course where I'd like to get you guys excited about how to predict why does things happen, and then we can go to complications. If I start with the complication, you'll be lost in the complication, we'll never understand the generality. Let's understand 80-90% of the cases where it works. Let's worry about the 10%, depending upon whoever is interested. If you worry about the 10%, the 90% will be lost. So therefore, I'm not doing it. Okay?
And so
Yes.
when we apply the RF pulse, does it equalizes the population?
I'll come to that today. That's a good question. Yes, that does happen. We will discuss about it today. So B effective is a little bit clear. You guys are able to understand how does the B effective come up? Okay, so let me continue talking about one more important aspect, which is the flip angle. NMR has many terms which are similar and confusing. For instance, magnetization and magnetic field. Similarly, I just defined a theta angle, which is called the angle. So basically, tilt angle is the angle between the static magnetic field B naught and the effective magnetic field B. If you apply RF, it's going to be away from B naught. It could be away from B naught, correct? Now, what is the flip angle? The flip angle is the change or the angle subtended position of the magnetization to the final position of the magnetization. You guys remember that the M naught was aligned along the B naught in the simulation? Then we applied something called a 90-degree pulse. What was 90-degree pulse? 90-degree indicates where you started, where you ended in terms of the magnetization. Correct? So the 90 degrees indicates a flip angle. The 30 degrees that we did, a small flip that came up, is called the flip angle. Okay? So this is the pulse that you apply, and the duration of pulse would determine what is the flip angle. And the flip angle goes by alpha, which is going to be omega r tau p. What is omega r? Omega r is minus gamma b effective. The textbooks writes BR, BR, BR everywhere, but I'm just writing as B effective so that you guys recollect that it's the effective magnetic field vector. Let's not complicate here. You guys remember that B effective is equal to B1 when off resonance doesn't exist. And you can understand this in many different ways. Here is where the tilt angle theta goes to 90 degrees. And we just saw B effective is given by B1 over sine theta. If theta is 90, you realize that these two are similar, same, correct? So when you have that, let's first understand it for the on resonance case and then worry about the off resonance case. This is a general equation that incorporates off resonance also. Let's now ask for an on resonance case. What will be the value of alpha, which is going to be given by omega 1 tau p. Why is it omega 1? Basically, omega 1 is minus gamma b1 tau p. Okay, what does this indicate? On resonance, when you're applying a pulse and making the magnetization move, if you keep applying the pulse without turning it off, the magnetization will keep processing about the effective magnetic field. Okay, so therefore, when do you stop the pulse determines the flip angle. Did that make sense? So basically, you started the magnetization along Z, and you're applying a pulse along Y for the current time being, let's assume. Applying along Y, and therefore the flip happens of the magnetization. And then you turned it off. You let it go for a certain time and you turned it off. Therefore, you got the 90 degree. Let's say you keep doing and then you turn it off. You got the 30 degrees. But let's say that you allow it to happen again and again and allow it until 180, then it will be a 180 degree pulse. You can have a 270 degree pulse, which is a minus 90 degree pulse. Then you'll say minus 90, why don't I just go from here to here by applying the opposite phase? You can do all that. We'll come to the understanding of phase later on, but overall, what I want to drive here is that the flip angle that's experienced by the magnetization depends upon the duration of the application of pulse. It's also called pulse width. Pulse duration, pulse width. What is a pulse? The RF pulse that you apply. That is the light that interacts with your matter M naught. So this is a characteristic of the light that we are talking about. So the duration of application would determine. We'll see the simulation again where we make it 180 degrees. Okay.
So in that simulation, the red vector was not actually.
What is that?
The red vector which was pulling the magnetization.
Yeah.
That was not.
That's correct. It's probably the torque that it was there. I made a mistake by saying it because I realized that's a yellow vector which we didn't see, which we'll see today. So Kaushal, right? Yeah. So Kaushal did point out to something that I had made a mistake in the previous lecture, where I said the yellow, or rather the red vector is what is making it move. Only when I did the simulation yesterday, I realized that the red vector indicates the direction of the force. Okay, it's not the vector that helps changing. That's because I did not turn on something here. So I did not turn B1. We just turned on B effective, which is the torque. So let me turn off everything. And then I'll show you the torque that we saw. So 90 degree hard pulse. So you see that is the red vector. So if you go to the rotating frame, let's go to equilibrium and then we hit it again. You see the red is the direction in which the magnetization gets pulled. That's not the direction in which you apply the pulse. So you're totally correct. I made a mistake the other day. And then now instead of saying torque, let's say we call it B1. Let's go to equilibrium. Now you'll see B1 as a yellow vector that helps things move. Did you see that? It was applied in perpendicular direction of the M naught, while the force, now let's also turn on the torque, which is the force that you end up getting, equilibrium. Now we are going to see three things. You're going to see the gray cylinder, an yellow B1 pulse that you apply, and a red torque that you see, which helps it move. So let's see it. Did you see that? So the yellow that you apply is perpendicular to M0, and the N0 moves in the cross product. So therefore it was starting in Z, let's say you applied in Y, therefore you go to X. Correct? Therefore, if you apply along X, you will end up along Y. Right? It will be minus Y, which we will see later on. So far, so good. So thanks for raising this to me. I'll come back. Okay, I could have shown the 180-degree pulse as well. So try the 180-degree hard pulse. The entire magnetization will go from plus Z to minus Z. And let's say you apply a 360-degree pulse. It goes all the way and comes back where it started. Don't ask what is the purpose of 360 degrees right now. We'll talk about it later. Each of them have their own purposes to establish. Okay, basically 360 degrees, 0-degree pulse. So this is the on resonance case we were trying to look at. Depending upon the strength that you end up applying, the duration might be longer or shorter. This is where we are talking about the soft pulse. The soft pulse has a selective pulse, which has a lesser magnitude of B1. If the magnitude is lesser, do you agree you have to apply it for a longer time? That's essentially what we did with the soft pulse. You realize the soft pulse took much longer to come there. That's because the B1 was weaker. For the same gamma, I'm assuming gamma is same. You're looking at proton NMR, let's assume. Gamma does not change. So at that point, what ends up happening? You have to flip 90 degrees, let's assume. You can either flip it with high B1 or low B1. If you have high B1, the tau p has to be small. In theory, for hard pulses, we try to have as high a B1 as possible, so the tau p is as small as it could be. Okay, let me give some numbers so that it helps you guys relate. So the B1 that we end up applying is generally around 25 kilohertz. And that somewhere translates to something like 10 microseconds. Truth be told, it's opposite. If you apply a 10 microsecond pulse at a certain power, it will be equal to B1 of 25 kilohertz. But for this course, let me tell it in a way where people will understand. And how is this determined? This is determined something called a TBP, time bandwidth product, where we apply something called a rectangular pulse, or a square pulse, however people want to call it. They call it the rect or the square pulse, which means that you apply the B1 for a certain amount of duration tau. Meaning that while you're applying the B1 is constant. You can always have shapes that come up. Let's not complicate ourselves with it until we go to the much later part of the course. For all practical purposes, you can imagine when I call a pulse, this is the pulse that we are applying. The radio frequency pulse has a constant amplitude and phase during its application. For such a pulse, for a rect pulse, the time bandwidth product, which means that bandwidth to pulse width. I'll tell you what is bandwidth as we go forward. Pulse width we just defined as tau p will be given as 1/4. This is a constant depending upon the shape that you take. So therefore, the bandwidth loosely translates to something like B1. The pulse width is the tau p that you have. So therefore, if you end up applying, so what is the bandwidth for a 10 microsecond pulse? 1/4 times tau p. For tau p equal to 10 microseconds, the bandwidth is going to be 1/4 times 10 multiplied by 10 power minus 6. Therefore, this is going to be 25 kilohertz. What does the bandwidth of excitation imply? The bandwidth of excitation implies how far from the carrier will the pulse be experienced. We just said that for ethanol, let us assume, I'm going to give some rough numbers. I'm not thinking about these numbers, just to give you guys an idea. If you keep the methylene proton at 0 hertz, which is the carrier frequency, this guy will be at, say, minus 1000 hertz for just as an example. And this guy will be at, say, plus 2000 hertz. Just as an example I'm giving. So therefore, the entire spectrum can be encompassed within 3000 hertz. Correct? So if you end up keeping the carrier here, this gives you an idea how far things go away from the carrier. So basically, this pulse will be affecting a change from 0 to 12.5 kilohertz on one side and 12.5 kilohertz on the other side. So this way you realize all your spins are within it, so therefore your excitation will be uniform. Okay, so we actually apply a pulse stronger than what is required, although it's a very weak pulse. We repeatedly say it's a weak pulse because it's just 25 kilohertz we are applying on a 500 megahertz spectrometer. And the 500 megahertz is omega RF. The omega RF will be set to 500 megahertz, while omega 1 will be set to 25 kilohertz. If you slowly realize I'm messing up symbols and units, this is commonly done in NMR. Sorry about it, but I want to keep up with the convention. Where the omega is given in hertz unit, omega should be given in radians. But we give it in hertz because it helps us understand. Omega RF will be matched with omega naught. So did that make sense? So this is the resonance part of NMR. What is nuclear magnetic resonance? You actually set your carrier transmitter frequency to the Larmor precision frequency. That's how you establish resonance, not by keeping an amplitude that has to match 500 megahertz. In theory, if you have 500 megahertz energy difference, you have to supply that much energy, right? You don't do that. You don't do that. You do something much less than that. Correct? You just make sure the precision frequency is matched and you apply a much smaller B1 and you end up affecting a change in the magnetization. What happens to the magnetization, we'll see in a moment. What happens in the quantum picture, we'll see in a moment. I just repeated what we did yesterday, but with a little more idea of the numbers and all that.
Carrier frequency 0 hertz.
It's not zero, it's relative. Wherever you keep, okay, sorry, good question. When I say 0 hertz, I'm trying to say it's on top of Larmor precision frequency. Sorry. Good point. In some ways, the rotating frame helps me forget 500 megahertz exists. So I went to a relative frequency unit. Okay, so this is what we entirely established by going to the rotating frame. I really don't have to worry about the 500 megahertz at all at this point. It's going to be there. It's always going to be there. It's never going to change. Why should I worry about it? It's the overall idea. Good question. It's not 0 hertz. It's 0 hertz from the carrier, where the carrier is at 500 megahertz. So that being done, let's move on to the next part. What is happening when you apply the 90-degree pulse? I'm writing it explicitly so that you guys also start to think about it. What is essentially happening is that let's first understand the equilibrium situation. What is the equilibrium situation? We are talking about two states that exist. And we said that population in one state is greater than population in the other state. This results in an M naught that's along Z. So in its own ways, this is the Z component of the magnetization. And what is the XY component of the magnetization at equilibrium? You might remember the XY component mutually cancel each other and you get nothing at equilibrium. So this is the equilibrium case. I'm going to call it EQ. Magnetization results because there is a population difference. The moment you end up applying a 90-degree pulse, what happens is that populations in alpha and beta become equalized for a 90-degree pulse. For a 180-degree pulse, the populations invert. We'll understand that later, but let me ask whether you're able to follow what I mean by when I say when you apply a 90-degree pulse, the populations become equal in the alpha and beta states. If that happens, what will be the Z magnetization? It'll be 0. Because Z magnetization came up due to population difference. Some people call it a polarization for this aspect. Since there is a population that results in a magnetization, this is also called polarization. Okay, but you realize that when you looked at the magnetization picture, the entire M naught came to XY plane. So you realize as law of conservation of something, here is magnetization. You got the M naught here, right? Oh, that's very interesting. Are we trying to apply an RF pulse and change the orientation of the alpha and beta states with respect to B naught? That's messed up, isn't it? Alpha and beta states are quantized. Quantum mechanically, those magnets cannot orient themselves in any other ways. This is what quantum mechanics tells you. Two possible states. These are the orientations. Take it and don't ask me anymore. B naught always exists. So what is happening when you apply B1 is a question. How does B1 affect the magnetization coming transverse? You can't change alpha beta states there wherever they are. So the answer lies in the fact of going back to the quantum mechanical picture, where you had a bunch of alpha and beta states. And we said P alpha is greater than P beta, which resulted in a net magnetization M0. Equilibrium. This is equilibrium. When you ended up applying this 90-degree pulse, what ends up happening is that it achieves two purposes. One purpose is to equalize population across the states. You can imagine this as the fact that the quantization along Z is now squashed because the B0 vanished. If the B0 vanished, what happens to the energy levels? They kind of apparently become degenerate. What happens when you become degenerate? Populations equalize. Yeah, but this is an apparent perception in its own ways in the frame that we are in. But at the same time, this pulse also achieves something very important, meaning that it starts to move. Let's assume that we applied a Y phase B1. So it starts to move all the spin vectors. They're still aligned at 54.7 degrees, but it allows for bunching of all the spin vectors to one axis, one part of it. Let me draw again so that it makes a bit more sense. They're still aligned at a 54.7 degrees with respect to B0. Once the populations equalize, the work done by the RF pulse is to pull all the spins to the same state. Yeah. So therefore, the alpha beta state still exists, but the populations are equal. Now you realize there are two vectors that are pointing along two different axes where the net resultant is along X, and therefore you generated the magnetization now along the transverse plane. This is a very tough concept to understand. NMR works in very weird ways. In most of the spectroscopy, it's all polarization that does the job. But in NMR, it is the phase coherence. What is phase? What is the meaning of the word phase coherence? Phase is what we said as the phi aspect of the alpha and beta states. And initially, the average phase was 0 because there are every possible orientation and they mutually cancel each other. Now, when you ended up applying the pulse, suddenly you allowed for all of the spin vectors to have the same phase. So this is called coherence. Coherence meaning everything in sync. So you generated a phase coherence by applying a pulse, which results in bunching of the alpha and beta spin vectors. Since their populations are equal, you get a net magnetization that's along the transverse plane. So if somebody tells you, you took the alpha state and you flipped the alpha state, that is wrong. Alpha and beta states do not flip. They are always where they have to be, which is at 54.7 degrees with respect to B0. On the other hand, what does your RF achieve is result in a phase coherence. So something that is at equilibrium is called polarization. Of course, anything that is not equilibrium is a non-equilibrium state. Do you realize that we had taken things away? So let me write again. So Z component is going to be M0. XY component was 0. Here Z component is 0. XY component is M0 for a 90-degree pulse. The magnitude of things will change if you apply a 30-degree pulse, where you won't change all of the populations to the XY plane. You change a little bit of it. That's the projection that you ended up seeing as a shadow in the simulation we did. You'll understand it has a sine alpha component to it. So alpha is 90, you have the maximum. Alpha is 30, you have less than the maximum, right? So far, so good. So you generate a signal in NMR spectroscopy with an RF pulse due to phase coherence. Okay. So now I hope, although both are M0, you guys are able to appreciate the fact that one comes due to polarization, which is population difference. Other comes due to phase coherence. The magnitude of M0 is the same, but the reason why they came up are completely different. The first one came up with no phase coherence and only population difference. The second one came up with no population difference, but only phase coherence. So these are, although they have the same magnitude, these magnetizations are kind of different beasts. You change one animal to another animal. Most importantly, you also realize you're not anymore in an equilibrium situation. If I ask students who are sitting in this class whether they'll sit in the same class all the time, that's not going to end up happening. After the class, you're going to go back to another class. You keep on doing this until you go back to your room. That's your steady state equilibrium. Your overall thermal equilibrium is probably back to your home. Correct? You're still in steady state equilibrium in your hostel rooms. You're not in a thermal equilibrium. Correct? So similarly, anything that you disturb away from its steady state or thermal equilibrium wants to go back to its steady state or thermal equilibrium. Everything wants to go to its thermal equilibrium, but when we stop it at a steady state, we call it a steady state equilibrium. So now you realize that you generated phase coherence. I made all you guys sit in the NMR course. You guys will not sit here if I give lecture for 4 hours. You'll start to dephase. You cannot concentrate and get the information. Similarly, the spin vectors, the moment you stop the B1 pulse, will not be phase coherent anymore. It will start to dephase with respect to each other. That's called decoherence. This has to happen because equilibrium is fully decoherent state. No coherence is equilibrium. So therefore, since you created coherence, it's a non-equilibrium state, it'll try to go back. Everything try to relax back. So that phenomenon is called relaxation. And since the magnetization that comes in the transverse plane versus the longitudinal plane are different animals, they have different relaxation rates. One is a population difference, other is a phase coherence. Right? So therefore, what did Bloch do? Bloch ended up saying the rate of change of magnetization along any of the axes depends upon how far you took it away from equilibrium. And he assumed a first order rate where M0 is the initial magnetization. For Z, you started with M0. And after pulse, you achieved MZ. If it's a 30-degree pulse, there's still non-zero along Z, magnetization along Z. So he says, how much ever you're far away is how fast it will relax. If I take you to a super tough course, you'll quickly quit the course and leave the classroom. On the other hand, if I give an easy course, maybe you won't leave at all. So depending upon how far I take you away from equilibrium, you want to relax that fast. In terms of exercise also, you can imagine. You do very heavy exercise, you have to wait for a little bit before you can repeat it. We do something light, you can keep doing it for a long time, like walking. Correct? On the other hand, if you are lifting heavy weights, you do some reps and you stop, get back, and then repeat it. You can't just keep on doing it. You will lose it. Correct? So similar is the idea. So Z started with the equilibrium equilibrium magnitude on M0, which is a constant based on the ferromagnetic ratio B0 and I. And then MZ is what you tilted it to. Of course, when you apply a 90-degree pulse, this goes to 0. And when you apply a 180-degree pulse, it goes to minus M0, which makes it 2M0. You realize 180-degree pulse, you push it all the way to the down, completely non-equilibrium state. Farthest away from equilibrium state as possible. If you take it that far, it will relax faster than from 90 degrees, than from 30 degrees, and so on. dmz over dt is R1 times M0 minus mz. This is the first order rate equation. Similarly, the transverse magnetization is also proportional to how far it is away from equilibrium. But what was its equilibrium? 0, correct? So he says this is going to be proportional to whatever you have to start with. Okay, I think I missed a minus sign here.
0 minus.
Yeah, right? Yeah, exactly correct. So there'll be your equilibrium was 0 and then whatever you have. Since therefore you get a minus sign. And he called this proportionality as a different proportionality constant, which is R2. Why R1 and R2 are different? Because these are different animals. The reason how magnetization comes along Z-axis versus X and Y are very different. Therefore, you can't have the same relaxation phenomenon. Okay? So the R1 is called the spin lattice relaxation parameter, relaxation rate. R1 is called the spin lattice relaxation rate. And R2 is called the spin relaxation rate. For the want of time within this course and complexity, I cannot go into why R1 comes out, how is R1 different from R2 and all that. Please take it from me. I hope I have convinced you that R1 and R2 are indeed different. R1 is where a spin interacts with its surroundings, which is why it's called spin lattice. These definitions come from solid state kind of a definition where they call the spin and anything around it is a lattice. But in solution state NMR, you don't have lattices, but you still have solvents which act as energy sink. It'll take any energy that you give it. It'll also give energy at some point, but right. But in this case, it took energy. Therefore, the energy from the spin gets dissipated to the surroundings, which is obvious. You heat a glass of water and keep it, it's going to relax back to room temperature. So it gives heat outside. So everything around the tumbler of water is lattice. This is what they are imagining it. And R2 is the spin-spin relaxation, where you have the coherence that exists. The coherence gets destroyed by if coherence exists in the neighboring spin or not. That's why it's called spin-spin coherence. The reason for why these end up arising is because although you say there's a constant B naught, there are small changes in B naught that exist within the sample itself. And there are disturbances that come to the B naught. So therefore, the homogeneity of B naught gets lost, and therefore decoherence happens. There are multiple reasons for that to happen, but I'm not going to go into the details of it. But I hope I have been able to make you guys accept that these two are different relaxation rates. And most importantly, what has been observed is that R2 is always faster than R1, meaning that the phase coherence you generated will die faster than the recovery of the longitudinal magnetization. You can imagine this to be a case where I teach you something, you'll forget this much faster than going back to your room. You'll be very happy going to your room and forgetting NMR, right? What happens faster? Forgetting happens faster. We'll ask questions tomorrow to figure out whether you remembered anything, right? It's something like that. So basically, the decoherence is much more faster than the spin lattice, this thing. So I'll just give you some numbers. R1 is 1 over T1, where T1 is the relaxation time. Depending upon textbooks that you follow, you will have slightly, either people follow time or rate. I will end up choosing different things depending upon what I want to teach. So T1 is the spin lattice relaxation time. T2 is a spin-spin relaxation time instead of rate. Okay. So just to give you numbers, T1 for some small molecules, like let's say ethanol, will be in the order of 2 to 3 seconds, while T2 will be in the order of something like, say, 0.5 to 1 second. This is for a small molecule. So meaning that T2 is shorter. If T2 is shorter, R2 is larger. R2 is larger than R1. That means R2 will kill, the coherence will be killed faster than the magnetization that comes along M0. So there will be a certain time at which the M0 will be more squandered in the transverse plane with not full recovery happening in the longitudinal axis. Does that make sense? I would like to take the last 5 minutes to simulate a little bit of what is this relaxation and what does this mean. But we go to the semi-classical picture again to end up doing this. So where are we right now? Are we on equilibrium or non-equilibrium? Why did you say non-equilibrium? Correct. I didn't apply anything. I started the simulation. It's doing this. So are we in equilibrium or non-equilibrium?
So in equilibrium, the M0 is pointing towards B0.
Is M0 pointing parallel to B0? Therefore, it's not equilibrium. Okay. At equilibrium, M0 and B0 are collinear. Since it's not collinear, it's a non-equilibrium state. Okay. Let's rewind back what we understood a little moment earlier. So now you guys will understand the plot that comes up on the right top. It's trying to give you the magnitude of MXY, which will be in white, and MX in red. Okay. And I can also have MZ, but we will complicate things one at a time. Now let me apply the 90-degree pulse. Keep watching what happens to MXY and MX. When you apply the pulse, immediately things increased. So the magnitude of MXY remains constant, which is square root of MX square plus MY square is still M0. That's why the white line does not change after the pulses come up. We have still not included relaxation. We are assuming there's no relaxation. Okay. So, and therefore, the signal ends up oscillating along the MX. This is how we end up measuring. Correct? Now, what is that we want to achieve right now? Let's try to understand relaxation a little bit. Okay. So we go to relaxation, and now they have set T1 and T2 to infinity, if you're able to see. That's why no relaxation is happening. So let's put some numbers. Let's put T1 as 4 seconds and then T2 as 3 seconds. Just for an example. Actually, we'll make it drastic. We'll make it 1 second. Okay, are we ready? What is that we have to look for here in the simulation? I apply the pulse, the bulk magnetization gets tipped, flip happens. After the flip happens, how long does it take for the shadow along the XY plane to disappear? And how long does it take for the gray cylinder to come back fully back to its thermal equilibrium? That's the exercise. Shall we do it? Are we ready? So I'm going to hit a 90-degree hard pulse. So now it's going to slowly go back to its equilibrium. Remember, it's first order rate kinetics. When does it finish? At infinite time. Okay, so it still wouldn't reach, it'll be 99.99999. It keeps on, 100 will be reached at t equal to infinity. So let's not worry about it. Let me repeat the exercise so that you guys understand what's happening. Hit. You're looking at the evolution of magnetization and not of spins. So don't misunderstand this. What are spins undergoing at this point? Population equalization and decoherence happening. Decoherence results in reduction of the shadow along the XY plane. Reversal back to the equilibrium population allows you to get the longitudinal magnetization. Okay, so now what we will do, I don't know whether I can completely shadow this. So only look at the shadow right now. Don't look at the gray cylinder. You see the shadow will slowly keep losing in the length. You see this? It's almost gone. Did you observe that? Let me repeat it. 90-degree pulse. You see the length of the shadow. As it keeps moving, becomes smaller and smaller. This precision is causing a lot of trouble, right? So therefore, what should we do? Go to the rotating frame. Thank you very much for the answer. So now let's do the same exercise. I went back to equilibrium. Now see the length of the shadow. You'll be able to follow much easily what's happening to transverse magnetization. Don't worry about the cylinder. Do you see that the transverse magnetization just kept on losing the length in its vector? So it's dying, correct? And at the same time, the longitudinal is trying to recover back. And there is a certain time at which the transverse magnetization has fully died, but the longitudinal magnetization has not fully come up. That's because of the difference that exists in T1 and T2 times. T2 is always shorter than T1. Okay, and this can also be understood. Let me repeat the same exercise. Now look at the top right portion of the simulation. I hit the 90-degree pulse. You started with the full signal, and you're able to see the transverse magnetization dying as a function of time. You have an oscillation and you have a relaxation that happens simultaneously. Let's go back to the situation when there was no relaxation to understand this. Infinity and infinity. We go back to equilibrium. When I hit it, if you guys might remember, at that point, the oscillation was constant and it was not dying. Okay, as the oscillation keep on going on and on and on, you'll be able to measure it. But in a realistic scenario where I go to equilibrium and then set transverse and longitudinal relaxation times to a certain number, you see that this oscillation also dies over a period of time. You see that? The oscillations are not of same amplitude. The amplitude gets decayed. The decay happens because of the relaxation. What I request you guys to do is to go back, solve the first order rate equations and understand what is the functional dependence of it. That's what we'll start the next week's class on. So please go back and read this to understand what did we establish, what are Bloch equations, and how does relaxation come up? How does a signal arise in NMR? Thank you very much.